Welcome to lesson 6.5, and in this final lesson of unit 6, we're going to take some time to go a little bit more in depth on this idea of the antiderivative. And so as a reminder, the antiderivative comes about when we are given a function that's already a derivative, say we're given f prime of x. The antiderivative is the name for f of x, the function that came before it. And so an example that would be a review from 6.4, given f prime of x, our derivative, equals the fifth root of x squared plus 4 over the fourth root of x cubed, let's find the antiderivative, or what we're actually trying to find the original f of x. And one thing we'll do is the same sort of rewrites that we did when we differentiated. So especially if we see roots like this, we're going to rewrite them as powers of x. So fifth root of x squared, this would be x to the 2/5 plus 4 times, and this is x to the 3/4, but in the denominator, we'll just go ahead and move it up in one step, and it'll be x to the negative 3/4. And working backwards, the notation for it, that is our integral sign, but without any boundaries. It's the indefinite integral with respect to x. Reversing the power rule, x to the 2/5, we would add 1 to go in reverse. So 2/5 plus 1, or 2/5 plus 5/5 would give me 7/5. When differentiating, we always multiply by the original exponent. Moving backwards, we're going to divide by the original exponent. Plus, this x to the negative 3/4, adding 1 to that, or adding 4/4, would become x to the positive 1/4. And again, we're going to divide by that original exponent. And the other thing is, we always have to leave open the possibility that there was a constant in the original function, because derivative of that constant would have been 0, and it would have gone away. So we denote that with a plus c. And this is our f of x. Cleaning things up a little bit, this will actually become 5 over 7 x to the 7/5 plus 16 x to the 1/4 plus c. And you can always confirm by just redifferentiating that function. And so as confirmation, f prime of x, using the power rule in the original order, the 7/5 times the 5/7 would be 1. And subtracting 1 from the exponent will give me x to the 2/5, which is what we wanted, plus the 1/4 times the 16 will be 4. And subtracting 1 from the exponent will be to the negative 3/4, and the derivative of that constant will be 0. And so like I said, we're going to go a little more in depth on this idea of the antiderivative. And first thing we're going to do is look at some antiderivatives for some common functions. And what I mean by that is functions that if I know I'm starting from the derivative, I should know the function that came before it. For instance, if I know f prime of x is equal to 1 over x, and I'm looking to integrate that, I'll get that f of x equals, and thinking of the function whose derivative was 1 over x should get us back to the natural log. A key thing on this one, remembering that you can't do the natural log of negative numbers, and realizing that 1 over x allows for both positive and negative numbers, we include an absolute value on that. And that's just to make sure the domains match up. And like on every antiderivative, every indefinite integral, we put a plus c. Our second common function that we should know the antiderivative for, looking at y prime equals e to the x, we'll integrate in this function here. The y prime will become a y, but the more important part, the integral of e to the x will just be e to the x. Remember, that was our one special function where the derivative equaled the original function. So moving backwards, it should make sense that we're going to end up right back at e to the x, and plus c. Looking at dy dx equals cosine of x will give us y being equal to, and think, what function had a derivative that was cosine? That should get us back to sine of x, and plus c. And finally, the derivative with respect to x of y being equal to sine of x. We'll integrate both sides of this, and we'll get back to y equals, and make sure you pay attention on this one. We're integrating the positive sine of x. What function had a derivative that was positive sine of x? That would have to be negative cosine of x plus c. One thing I want to remind us of, which I put all the way back on our trig derivatives, was our little wheel of trig, where we think about the unit circle and remembering where sine of x was positive cosine of x was positive, we had a negative sine of x here, and a negative cosine of x. When we wanted to differentiate, we moved clockwise around this circle. The blue here means taking the derivative with respect to x. And so it should follow that if I want to go backwards and find antiderivatives, I would just move backwards around this circle and go counterclockwise. So again, if we use that, the integral for cosine of x went counterclockwise back to positive sine of x. The integral for positive sine of x went backwards to negative cosine of x. And just make sure you find some way to keep track of when you're going to have to change signs both on differentiating with these two trig functions and when integrating. And here's what we're going to wrap up with, talking about what are known as initial conditions. And all we're going to be thinking about in this is getting the ability to find a value for the plus c in all of these integrals that we've been talking about. Because on all of those, we've left open the possibility that we could be adding any constant. What's going to lock in one particular constant? And so let's look on the first example, where f prime of x equals 3x squared minus x plus 4, and f of 2 equals 8. Well, the directions say find the function f that satisfies the given condition. But the key thing is the first direction was to just find a function f, find our f of x. And we'll get that from integrating the function given to us. F of x will equal integral of 3x squared. Well, the square will become a cube. We're going to add 1 to it. Divide by the new exponent. 3 divided by 3 would just give us 1. Minus this x to the first power will become an x to the second power. And dividing by that original exponent, we'll get a negative 1/2. Plus the integral of 4. The easy ones are the constants. That'll be a 4x. And plus that c. Well, what I'm going to say is, I know that f of 2 equaled 8. I know one particular point on this original function. And what that's going to allow me to do is say f of 2 equals 2 cubed minus 1/2 2 squared plus 4 times 2 plus that unknown constant actually has a value that we know. The whole thing has to equal 8. And so simplifying this, we would have 14 plus that constant equals 8. And the constant itself then would have to equal negative 6. So the specific original function we are dealing with in this problem is f of x equals x cubed minus 1/2 x squared plus 4x minus 6. Again, having just that one point allows us to get rid of that uncertainty surrounding this constant and give us one nice defined function. For our second example, f prime of x equals 3 square root of x plus 3. I'm immediately going to go ahead and rewrite this one as an x to the 1/2. And our initial condition to help us get rid of that plus c, f of 1 equals 4. So integrating both sides, we will get f of x equals, and that x to the 1/2, adding 1 will be x to the 3/2, and dividing by that exponent of 3/2 will get us back to 2, plus 3x, and then our plus c. And substituting in our initial condition, f of 1 will equal 2 times 1 to the 3/2 plus 3 times 1 plus that constant value, and doing that has to give us a result of 4. So 2 times 1 to the 3/2 will just be 2 overall plus 3. We'll know that 5 plus c equals 4, and so our constant has to be negative 1 based on that initial condition. And therefore our specific original f of x function equals 2x to the 3/2 plus 3x minus 1. And so let's look at one problem where we're going to have an extra step involved and wrap up with an application of this idea of initial condition. So our instructions are to find y if y double prime, so our second derivative is given here, equals cosine of x. And what we're given is y prime of pi over 2 equals 2, and y of pi over 2 equals 3 pi. What we're going to have to think about is if I want to get all the way back from y double prime to y, we're going to have to integrate twice. And so where we're going to start, we'll start with y double prime equals cosine of x and integrate from there. But we can only jump up one level. The function that came before y double prime is y prime. And the integral of positive cosine of x is positive sine of x plus c. Now we want to integrate one more time to get back to our original y, but it'd be really nice if we get rid of this constant before we do that. Otherwise, we're going to end up with this constant and another one from our second integration. Well, note we're told a condition about y prime. Y prime of pi over 2, which would be sine of pi over 2 plus c, has to equal 2. Sine of pi over 2 is a positive 1, which is going to leave c to also be a positive 1. And our actual y prime equation is going to be sine of x plus 1. Integrating y prime will give us that y that we were looking for, and it will be equal to the integral of positive sine of x is going to be negative cosine of x, plus the integral of 1, which is x, plus another constant. We'll call this capital B and just move back a letter. But again, we know a condition for y as well. We know that y of pi over 2 would be negative cosine of pi over 2 plus pi over 2 plus this b, and that has to give us 3 pi. Well, cosine of pi over 2 is going to be 0, plus this pi over 2 plus b, that's going to give me my 3 pi. B itself will be 3 pi minus pi over 2, or 5 pi over 2. So our original y equation and our final answer will be negative cosine of x plus 5 pi over 2. And like I mentioned, we'll wrap up with our application of this initial condition idea and get everything back to one of the overarching concepts of calculus, which is motion, working with position, velocity, and acceleration. So a particle moves along the x-axis left and right with an acceleration of a of t equals 12t minus 4. So I'm given this as my acceleration function. The particle's velocity is 18 centimeters per second at t equals 2. Or put in function notation, whatever our v function is, v of 2 will equal 18. The initial position of the particle is 8 centimeters. One thing we're going to need to get down is initial in any problem like this is going to mean at time equals 0. So when we get our position function, which we'll call x of t once we get there, x of 0 will equal 8. And what we want is we want the exact position of the particle at t equals 3. So we want to know what x of 3 equals, which would be really easy if we had an x function. Since all we started from was a of t, and knowing we want to get back to x of t, we just got to remember the relationship between these three functions. To go from position to velocity was the derivative with respect to time, and same thing to move from velocity to acceleration. So if that's the case, going reverse, it should follow that we're going to have to integrate twice, just like we did in the previous example, but this time with a story attached to it. So we'll start from our a of t function and integrate both sides. This will get us back to our velocity function. Integral of 12t will be 6t squared. Integral of this 4 will be a 4t plus c. And we'll use our initial information about velocity to help us out. We know that v of 2 will equal 6 times 2 squared minus 4 times 2 plus this constant, and our result needs to be 18. This will simplify to 16 plus c equals 18, and our c value is 2. So our actual velocity function is 6t squared minus 4t plus 2. And now we'll go on and integrate both sides of that to get to our position. Integral of v of t will be x of t, and integral of 6t squared will be 2t cubed. Integral of minus 4t will be minus 2t squared. This plus 2 will be a plus 2t, and again, plus some other constant. Again, we'll move backwards in the alphabet and go with a plus b. The information we know is that x of 0, which would be 2 times 0 cubed minus 2 times 0 squared plus 2 times 0 plus this b, has to equal 8. And the nice part, anytime you're given something at time 0, is you get a lot of stuff to cancel out. Our b value is actually just 8. our original position function is 2t cubed minus 2t squared plus 2t plus 8. And now we can answer our final question. We wanted to know our position at time 3. Now we just get to plug 3 into our position function and simplify it to get our final answer. And so everything we're doing is just doing the same position, velocity, acceleration stuff we did with derivatives, just in reverse. And our position at time equals 3 will equal 50, and the units on that being position will be whatever our length units were, in this case, centimeters. So that'll do it, not just for lesson 6.5, but for all of unit 6. So please make sure, review and summarize these notes. Make sure when you get into the practice, we're especially paying attention to problems involving position, velocity, acceleration, and start to make sure that you're reviewing all of the unit 6 sections, as you should be planning on having a test soon. When you're ready, move on to the 6.5 practice, and thank you for watching.